This is ME12 forced air intake by Brian Larsen, Josh Hunter, Brady McConnell, and Joseph Zona.
For some quick background information on our project, the Penn State Barron SVE Club has been competing in the Shell Eco Marathon for the last 5 years. Since the current engine setup is new to the team, much has been desired for engine performance and efficiency. The current sponsor of this project is the club president who has been a member for the last 3 years. He has enlisted the help of ME12 to help design and implement a forced air intake to help increase the overall efficiency of the engine and increase the miles per gallon achieved by the car during competition.
Okay, so for our final design, we decided to go with a longer pipe style, and we have to incorporate the 180 to act as a sort of kitchen sink to catch any debris that comes in, due to Shell Eco Marathon regulations only allowing us to have no mesh. Most connection points were brazed. The clamps with the elongated ears on them are held together by bolts to make an airtight connection. And the scoop, since it is a different material from the rest of the intake, we had to use a different method to adhere it.
So for our project, we did three major forms of technical analysis to try to help verify our design. The first being vibrational analysis. This is very common for our scenario only because we are trying to connect a vibrating body, being the engine, to a non-vibrating body, being the frame of the car itself. So we had to do this to ensure that we wouldn't experience any structural failures at some key points in our design to allow for no premature failure. The second form that we did was heat transfer CFD. We tried to ensure that we would experience as minimal amount of temperature increase due to the ambient environment as possible. And over here with this picture, you can see a slight contour of the z-axis, or the zy plane, sorry, of our pipe system. And you can see how the temperature develops going through the pipe. And lastly, we did a aerodynamics drag CFD to ensure that our scoop on the outside of the vehicle wasn't causing too much drag to henceforth mitigate the efficiency that we would be hopefully bringing to the vehicle.
To test the efficiency of our design, a circuit was constructed in the AMIC parking lot. 8 laps around the parking lot were done, and that equates to roughly 2.25 miles. The amount of fuel done per run was recorded using a burette, and using that fuel recorded and the total distance, we are able to calculate the miles per gallon for each of these runs. Looking at the table, you can see that between run 1 with the scoop on and the scoop off, adding the scoop increases the efficiency, and the same can be seen for run 2. The reason run 2's efficiency is much lower than run 1 is because the car was put under heavier loads for these tests. Based on our results, it is conclusive that the scoop and the intake increase the efficiency of the car.